Hello students, I hope you all had a great Labor Day. This video will cover week 3, resultant of coplanar force systems using the component method. We will look at Unit 3, Part B, which will cover the resultant of coplanar force systems to determine the parameters of the resultant of 3 or more concurrent forces using the methods of components. Please read chapters 2, sections 2.3, pages 29 through 41 in your Statics and Strengths of Materials for Architecture and Building Construction class textbook. Please note that throughout this course, some of the following slides will contain only parts of the class textbook for your reference and for your convenience. Please refer to your textbook using the page numbers shown for more information. And below is the bibliographical information for your textbook. We will begin with page 29. 2.3 Force systems. Resolution of forces into rectangular components. A reverse effect of vector addition is the resolution of a vector into two perpendicular components. Components of a vector or force are usually perpendicular to each other and are called rectangular components. The x and y axes of a rectangular coordinate system are most often assumed to be horizontal and vertical, respectively. However, they may be chosen in any two mutual perpendicular directions for convenience. A force F with a direction theta from the horizontal x-axis can be resolved into its rectangular components, Fx and Fy, as shown in figure 2.4. Both Fx and Fy are trigonometric functions of f and theta, where f of x is equal to f cosine of theta and f of y is equal to f sine of theta. In effect, the force components Fx and Fy form the legs of a parallelogram, with the diagonal representing the original force F. Therefore, by using the Pythagorean theorem for right triangles, we can say that F is equal to the square root of Fx squared plus Fy squared, and tangent of theta is equal to f of y divided by f of x, or that theta is equal to the tangent inverse of f of y divided by f of x. Here's a reminder of what the Pythagorean theorem looks like when using or finding forces and its x and y components. The opposite side is like Fy to the angle theta, and the adjacent side is f of x to the angle theta, and the long leg, or the hypotenuse, would be the force. We can then derive f of y is equal to the force times the sine of theta, f of x is equal to the f times the cosine of theta, and the tangent of theta would be equal to the vertical side divided by the horizontal side, or f of y divided by f of x. Let's take a look at Class CAD practice drawing problem number 5. Problem 2.8 reads, a clothesline with a maximum tension of 150 pounds is anchored to a wall by means of an eye screw. If the eye screw is capable of carrying a horizontal pulling force, withdrawal force, of 40 pounds per inch of penetration, how many inches L should the threads be embedded into the wall? The solution for this problem is notice that the direction of the force F is given in terms of the slope relationship. The small slope triangle has the same angle theta from the horizontal as the force F makes with the x-axis. Therefore, we may conclude that both the small slope triangle and the large triangle, as shown in a tip-to-tail diagram, are similar. Let's look at the practice analytical solution. The image on the next slide will show the AutoCAD drawing of three forces. The first one, shown in yellow, will be force F, which is tension force from the clothesline. A pair of lines can be drawn per the rise and slope of 3/4 to get the line direction, or we can find the slope by finding theta with the tangent inverse function of 3/4. We find that theta is equal to 37 degrees. Shown in red will be the counteracting horizontal force L. We find this one by using theta again, which is equal to 37 degrees, and F is equal to 150 pounds. And you'll remember, to find f of x, we will use f times the cosine of theta. F of x will equal to 150 times the cosine of 37, and we find f of x is equal to 120 pounds. Then we find the unknown embedded length by using L equals to 40 pounds per inch, where f of x is equal to 120 pounds, and divide by 40 pounds to find L equals 3 inches. And number 3, we'll show the unknown embedment length of L equals 40 pounds per inch, and is shown as a green arrow pointing left, attached at point 0, centered above the bolt's eye. To the clothespin is a tension rope force, F equals 150 pounds, pulling down to the right at an inclination of 3/4. And here we see what I just explained, where first we find theta by the tangent inverse of the rise over run, and we also find the f of x, which is the counteracting horizontal force of the force F equals 150 pounds. So that one would be equal to 120 pounds on the horizontal. And then we take a look at the unknown embedded length, and we use L is equal to 40 pounds per inch. With this, we find that f of x is equal to 120 pounds, and then we divide by 40 pounds, and L is equal to 3 inches. Let's take a look at Class CAD practice drawing problem number 6 on page 32. This problem will show us the resolution of forces into the x and y components. Problem 2.6 says, determine the x and y components of the force F shown. So here we see force F is equal to 1,000 pounds. We do not need to worry about the cantilevered beam or the horizontal support the beam has. All we will do is focus on F is equal to 1,000 pounds and find the x and the y components. So let's take a look at the practice analytical solution. The image on the next slide will show us the AutoCAD drawing of force F. Shown in the green arrow, we see force F, which is at the cantilevered beam end. We have a pair of lines that can be drawn per the rise and a slope of 3/4 to get the line direction. Or we can find the slope by finding theta with using the tangent inverse function of 3/4. We find that theta is equal to 37 degrees. Shown in a magenta hidden line we find the horizontal force component, or F of x. We do this by using theta is equal to 37 degrees and F is equal to 100 pounds. And for this part, we will use the F of x function, which is equal to the F times the cosine of theta. And then we plug in the numbers. F of x is equal to 1,000 times the cosine of 37, and we find F of x is equal to 800 pounds. And then you will see in blue hidden lines the vertical force component, or F of y. We will find this one by using theta is equal to 37 degrees and F is equal to 1,000 pounds. We use our function F of y is equal to F times the sine of theta, where F of y is equal to 1,000 times the sine of 37, and we find that F of y is equal to 600 pounds. Here is the illustration. Again, this is the practice solution or the analytical and graphical solution demonstrated. So we see here our force F shown in the green arrow, and it represents F is equal to 1,000 pounds. Then we find F of x, which is the horizontal component, by using the function F of x is equal to F cosine of theta. And we find that after plugging in our F equals 1,000 pounds and our theta is equal to 37 pounds, we find F of x is equal to 800 pounds. And then, of course, lastly, we find the F of y component, or the vertical component, with the function F of y is equal to the F times the sine of theta, where F is equal to 1,000 and theta is equal to 37. We find that F of y is equal to 600 pounds. Next, let's take a look at class CAD practice drawing problem number 7 on page 32. Problem 2.7 reads, if a hook can sustain a maximum withdrawal force of 250 newtons in the vertical direction, determine the maximum tension T can be exerted. Let's look at the analytical solution. On the image in the next slide, you will see in dark blue the maximum withdrawal force of 250 newtons in the vertical direction. To determine the maximum tension T that can be exerted, and to better orientate the triangle to find F of y and F of x sides, use instead 80 degrees. 80 degrees would be down to the bottom right side of the triangle rather than the top left side of the triangle. You can see here in this demonstration how if we were to technically reverse the theta angles, we would have to use the opposite and adjacent sides reversed as well. And therefore, again, if we would use 10 degrees as our theta, we would need to find F of y, with F of y is equal to F times the cosine of 10 degrees, again, which would be up here because that would be the adjacent side. And you will see in light blue, we see tension force T that is pulling down to the right at an inclination of 10 degrees from the vertical. And to find T, we use F of y is equal to the sine of theta, or 250 is equal to T times the sine of 80 degrees. And therefore, 250 divided by the sine of 80 degrees is equal to T. And we find that T is equal to 250.8567. To start off, the max vertical withdrawal force, or the adjacent side to theta, is F of y is equal to 250 newtons. 250 newtons. And to better orientate the triangle to the F of y and F of x sides, again, be sure to use theta is equal to 80 degrees, not the 10 degrees up here. And then to find t, we use f of y is equal to f times the sine of theta, or 250 is equal to t times the sine of 80 degrees. And then we do the math and we find that t is equal to 253.86. And lastly, again, notice that if we were to use 10 as our theta, we need to find the opposite of sine, which would be the cosine, right? So we would find f of y with fy is equal to f times the cosine of 10 degrees. And just for a quick refresher, we see here our reference triangle for finding f of y and f of x. When we have theta at the bottom right-hand corner, the opposite side of theta, in this case, would be y. So you can see that if we were to move theta from the bottom right corner to instead the upper left corner, the opposite side to theta here would be f of x. Okay, so that's why, again, we reverse the sine and the cosine when we have to switch around the theta. So to better be able to visualize which function you will use, I do recommend that, if you're given an angle up here, rather than using this angle as your theta, instead find the angle down here and use that as theta. Let's now look at Class CAD practice drawing problem number 8. This is on page 32, and problem 2.8 reads, a roof purlin supported by a rafter must support a 300-pound vertical snow load. Determine the components of P perpendicular and parallel to the axis of the rafter. So if you look at force P, we want to find the component of force P that is perpendicular to the axis of the rafter. And then we also want to find the component of force P that would be parallel to the axis of the rafter. Let's take a look at the analytical solution. The image on the next slide shows the steps to determine the components of the orange vertical line, force P, which equals 300 pounds, perpendicular and parallel to the axis of the rafter. To find the angle theta of the vertical force P to the axis of the rafter, first find the angle of the rafter to the horizontal plane. To do this, use the slope and find theta by using the tangent inverse function of 4/12, or 4/12. We find the angle of the rafter to the horizontal plane is 18 degrees. Force P is vertical, and if we subtract the 18 degrees from the right angle created by force P and the horizontal, we find that theta is equal to 72 degrees by subtracting 18 from 90. And then in blue, we see Px, or the horizontal component of force P. If P is equal to 300 pounds and theta is equal to 72 degrees, by using the function f of x is equal f times the cosine of theta, or in this case, P of x is equal to P times the cosine of theta, we have Px is equal to 300 times the cosine of 72 degrees. And we find that Px is equal to 94.87 pounds. Next, in red, we find the Py component of force P. If P is equal to 300 pounds and theta is equal to 72 degrees, by using f of y is equal to f times the sine of theta, or in this case, Py is equal to P times the sine of theta, we find that Py is equal to 300 times the sine of 72 degrees. So let's take a look at what this all means graphically. We have force P that is on the vertical, and it is equal to 300 pounds. And then the first thing we have to do is find the angle between the rafter axis and the horizontal plane, that is 18 degrees. Now, if you can see, we have between the force P, that's vertical, and the x-axis, we have 90 degrees. So in order for us to find the angle between force P and the rafter axis, we subtract 18 from 90 degrees, and we have 72 degrees. Next, we're going to find px by using the function px is equal to f times the cosine of theta. And we find that px is equal to 94.87. And to find py, we use py is equal to f times the sine of theta, or py is equal to p times the sine of theta. And we find that py is equal to 284.60. That we know how to decompose a vector into its x and y components, let's look at how we would add a vector analytically using the component method. We will read page 33, vector addition by the component method. As was shown in the previous sections, vectors may be added graphically by using the parallelogram law or the modified tip-to-tail method. Now, with the concept of resolution of vectors into two rectangular components, we are ready to begin the analytical approach to vector addition. The first step in the analytical approach involves resolving each force of a force system into its respective components. Then the essential force components may be added algebraically as opposed to a graphical vector addition to yield a resultant force. It is important to keep in mind that the vertical analytical addition will be using the sign of components. The x component of the force vector can be positive or negative. If it points to the right, it is positive. If it points to the left, it is negative. The y component of the force vector can be positive and negative as well. If it points up, it is positive, and if it points down, it is negative. Here we see a graphical representation of what this looks like. So assuming we have force 1 in what would be quadrant 2, again this is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So we're looking at F1 in this case. The y, or f of y, would be found by f of sine of theta, and it would be a positive sign. Again, starting at 0, we go up. And then the x, or f1x, would be negative. Again, if we have the center point here starting at 0, and we move to the left of the number line, we go into the negative sign of x. Now looking at f of 2 in quadrant 1, we see that f2y can be found with f times the sine of theta, and f2x can be found with f times the cosine of theta. Both of these signs would be positive. Again, if we were to start here at 0, moving up, or to the right, both our f of y and our f of x would be positive. Looking at force number 3 in the fourth quadrant, we can see that if we start here at 0 and we move downward in the number line, we're going to have an Fy sign. If we move to the right, we will see an F of x that is positive. And we can find these by F of 3y is equal to F sine of theta, and f of 3x is equal to f cosine of theta. And looking at, can see how if we start at the center of the graph at 0, and we move to the left of the number line, the x component will be negative. And if we move down, the y component would be negative. And we can find f of y, or f for y, is equal to f times the sine of theta, and f for x is equal to f times the cosine of theta. Looking at the vector analytical addition and component method, we can see how the sum of f of y would be the accumulated sum of all the Fy components of different forces. It can be also stated as the F resultant Y is equal to all the forces Y components, where Ry is a resultant or vertical component. And then we have the sum of f of x, which is equal to the sum of all the x components of the forces. It can also be stated as Frx is equal to the sum of all the forces x components, where Rx is the resultant horizontal component. In some problems, it is necessary to develop or set up equations for a system of linear equations explanation, for when you have two unknowns, develop an equation and substitute your variables in another to replace and eliminate one unknown. You can click at the bottom of the PDF for a link. So looking back at how the Pythagorean theorem can be used to find the x and y components of a force, with the function f is equal to the square root of f of x squared plus f of y squared, we can see how it applies to the vector analytical addition and the resultant r. So using the Pythagorean theorem, we can say that the force resultant is equal to the square root of the force resultant Rx squared plus the force resultant y squared. So let's take a look at some examples. We'll start with ClassCAD practice drawing problem number 9. This one is on page 35, and this is problem 2.9. These are example problems for vector addition by the component method. And problem 2.9 reads, an anchor device is acted upon by two forces, F1 and F2, as shown. Determine the resultant force analytically. To begin the practice solution, or analytical solution, let's solve first for F1. So first, we find the vertical and horizontal components of F1. Graphically, we can easily see that by adding dimensions, we can quickly find the f of y and f of x components of F1. To analytically solve for F1 force, we can start by finding theta, or theta of force 1. We can use the tangent inverse function of 1 over 1, which would be the rise and run, or 45 degrees. And then we will move on to finding the f of y component. F1y is equal to F1 sine of theta. And we find that by plugging in the 20 from our force 1 times the sine of 45, which is our theta, we find that F1y is equal to 14.1421. Now to find F1x with F1x is equal to F1 cosine of theta, we find that F1x is equal to negative 14.1421. Don't forget to add the negative sign. Remember, the f of x is traveling here in a left direction. We will find the vertical and horizontal components of F2. To find theta, you can use the tangent inverse function of 5 over 12, which is our slope, and that is equal to 23 degrees. You can find f2y with the function f2y is equal to f2 times the sine of theta. And we find that f2y is equal to 3.9073. Next, we find f2x with the function f2x is equal to f2 times the cosine of theta. We find that f2x is equal to 9.2050. Now that we have found both the x and y components of our forces, F1 and F2, we can use that information to find the components of the resultants by algebraically summing up the f of y components and the f of x components. So you will see here we have the sum or the resultant Fy forces. We have F1y and F2y. When we sum these up, we find that Fry is equal to positive 18. And then we find that the F of x is equal to F1x plus F2x. So again, this is the addition of the f of x components. And we find that the F of x is equal to -5. Once we have found the Rfy and the Rfx components of our resultant, we can now find the direction of the resultant by using the inverse tangent function of 18.0494 divided by 4.971, and we find that our theta here would be equal to 74.7019. Also, be sure to notice that if we were to change the precision, we get something slightly different. Like, for example, if we have the inverse tangent of 18 over 5 versus 18.0494 over 4.9371, we have that the angle theta is equal to 74.72.88. The reason why I point that out is because AutoCAD is very precise, and the last step is to graphically back check our resultant. And we do this by creating a tip to tail graph, beginning with force 1 and then stacking force 2, and then closing up our polygon with a line beginning at the beginning of our first force and ending at the end of our last force. We find that our resultant would be equal to 18.6467 K. Let's now look at Class CAD Practice Drawing Problem number 10. This one is on page 38. It is problem 2.11, and it reads, a block of weight W is equal to 500 newtons and is supported by a cable CD, which is in turn suspended by cables AC and BC. Determine the required tension forces TCA and TCB so that the resultant force at point C equals 0. Alright, so to begin, what I did first is kind of draft the directions of the two unknown forces, and then I also drafted the TCD, which is what we know. So let's go ahead and take a look at TCD. We know that TCD is equal to 500, right? Let's be sure to note that TCD has no x component, right? There's no angle here. It only goes directly downward. So we know there's no change in the f of x here. We only know that there's an f of y change. And then again, looking at the direction, we know that it's going to be a negative force. So again, be sure to note that TCD has no x component. Therefore, TCD will equal our TCDY component, which is equal to, again, negative 500. And also note that TCDX will be equal to 0. And then again, don't forget to add the negative sign. Next, let's take a look at TCA. First, we will find the vertical and horizontal components of TCA. Given that we do not yet know the force value for TCA, and we only know the directions, we will use variables for now. First, to find the theta of TCA, we can use the tangent inverse function of 8 over 6, which is our rise and run. And we find that theta of CA will equal to 53 degrees. 53 degrees right here. Next, let's find TCAY, that is the vertical component. We can do that by using our function TCAY is equal to TCA, which is again a known, times the sine of 53 degrees. So we solve for the sine of 53 degrees and find that that equals to 0.8. And then we set up our first function here, that is TCAY is equal to 0.8 TCA. Now, let's look at how to find TCAX. We begin with our function TCAX is equal to TCA, the force, times the cosine of theta at CA. And we find that TCAX is equal to negative 0.6 TCA. Again, don't forget to add the negative sign here because our X component will travel towards the left. Let's go ahead and take a look at TCB. To find the vertical and horizontal components of TCB, given that we do not yet know the force value for TCB, and we only know the direction of TCB, we will also use variables for now. So first, we begin with theta. In this case, theta is given as 30 degrees from the horizontal. And we find TCBY, which is the vertical component. We find that by using the function TCBY is equal to TCB sine of theta. And we find that TCBY is equal to 0.5 TCB. And then we find that TCBX with function TCBX is equal to TCB times the cosine of theta. We find that TCBX is equal to 0.866 TCB. All right, so let's see what this all means when we put it together. So first, we find the components of the resultant. We do that again by adding all our y components. So we have RFY is equal to TCAY plus TCBY plus TCDY. We set that equal to 0 because our resultant is equal to 0. And we have 0.8 TCA plus 0.5 TCB minus 500. Then we add 500 to each side to cancel it here. And we end up with 500 is equal to 0.8 TCA plus 0.5 TCB. Note we have two unknown variables, TCA and TCB. Then let's look at the X components. We will find that the resultant X component is equal to the sum of all the force components. And therefore we have 0.6 TCA plus 0.86 TCB plus 0. And we find that our resultant's X component will be equal to negative 0.6 TCA plus 0.866 TCB. Note again, we have the same two unknown variables as we did with R, F, Y. In this problem, it is necessary to develop or set up equations. For a system of linear equation explanation, for when you have two unknowns, develop an equation and substitute your variables in another to replace and eliminate one unknown. So let's see here. We now have our two equations. This one right here and this one right here. So we combine those. So let's set this up. We're going to solve for one variable using the set of linear equations. We start off with 500 is equal to 0.8 TCA plus 0.5 TCB. And then we also have 0 is equal to 0.6 TCA plus 0.866 TCB. So let's go ahead and start with 0 is equal to negative 0.6 TCA plus 8.66 TCB and solve for TCA. We first add 0.6 TCA to each side, and then we divide by 0.6 on each side. And we find that TCA is equal to 1.44 TCB. Now we substitute for TCA and solve for TCB. To begin, we set up the equation. 500 is equal to 0.8 TCA plus 0.5 TCB. We substitute for TCA and we now have 500 is equal to 0.8 times 1.44 TCB plus 0.5 TCB. Then we combine like terms and solve for TCB and find that TCB is equal to 303. Then we use TCB to solve for TCA, and when we plug it in, we find that TCA is equal to 1.44 times 303. Therefore, TCA is equal to 436. And to finish off, we end with a back check with a tip-to-tail graph, making sure that the polygon closes with our three forces. That was the end of week 3 lesson. Please be sure to take quiz number 2, due September 13, 2020. It will be available on Blackboard for week 3 assignment folder. The test will be a fill-in-the-blank portion on Blackboard that will consist of the following statements. You will also have assignment number 2, due September 13. Assignment number 2 will include problems 2.9, 2.11, and 2.12 found on pages 40 and 41. Solve the problems from your textbook with analytical solutions using the force components and check graphically using the tip-to-tail method. Use the AutoCAD class assignment templates for creating your drawings, and remember to annotate your drawings accordingly. The assignment number 2 consists of question 2.9, 2.11, and 2.12.